Welcome to lesson 2 of Puzzles to Exercise the Mind. I want to review a little bit on prime numbers. We'll have a short puzzle later concerning prime numbers, but let's do a review first. So a prime number is a positive integer, a whole number sometimes is used, or a natural number is even more common. And it has only two divisors, itself and 1. So the first prime number is 2, and in fact that's the only even prime number. Then all the other ones are odd numbers, 3, 5, 7, 11, 13, 17, 19. It turns out there's an infinite number of primes. That's a relatively easy proof. I'm not going to provide it here, but that's been known for a long time. Also known for a long time is a basic theorem about factorization. Any positive integer can be written uniquely as the product of prime powers up to order, so you can always reorder things here, but in terms of order, say from smallest factor to largest, there's only one way to do that. I have an example here. 10,780 can be written 2 squared, which is 4, of course, times 5 times 7 squared, which is 49 times 11. So you may want to try as an example just to test your skills, 323. And if you need some help, there's a calculator here. I'll put the link in the description to this video so you don't need to copy it down. But there's a lot of these on the web actually, but this is just one that you might want to use. That'll take a very large number actually. I forget how large, but certainly much bigger than 323, so you can check your answer there. The prime number game. So here's a simple game using prime numbers. We have 5, 7, 11, 13, 17, 19, and 23. The puzzle is to take each one of these numbers and put them in these circles. So one number per circle. And the sum across this top row needs to equal the same as the sum across the bottom row and the same as the sum across this diagonal and this diagonal. So there's 4 different sums. They all need to equal the same number. And I'll give you a hint. The sums are 41. Your task is to figure out how to place these 7 numbers in the circles in order to get everything to add up to 41. And I have the answer at the very end of this slide set. So you can check your answer there. If you get stuck, you can try there. This slide and the next few slides are more in terms of educational material and not so much in terms of any specific puzzles I'm proposing to the listener. So the first thing I want to mention here is something called Mersenne primes. They were discovered, or at least named after Mersenne, a French friar who studied such primes in the 17th century. And a Mersenne prime is a prime of the form 2 to the p minus 1, where p is a whole number, positive whole number. And we have a few examples down here. 2 to the 7th minus 1 equals 127, which is in fact prime. So that's one of the smaller Mersenne primes. And then just to show you that not every thing of this form here is a Mersenne or is a prime. So you have 2 to the 11 minus 1, that gives you 2047, and that's a composite number. It's 23 times 89. So that's not a prime number. And I just put a reference down here. There's quite a bit of information in the Wikipedia article on this topic. The largest known Mersenne prime was discovered on October 12, 2024 by something called the GIMS project. I'll explain that in a minute. The number itself was 2 to this very large number here, minus 1. And when you expand this out, you actually get over 41 million digits. It's published in a book. This is the cover of the book. I got this from Amazon. Not the book, but just the picture of the cover. It's 960 pages long, and you could buy it for $42.98. I don't know how much interest it would be, because it's just a very small font, and it's the listing of all these digits, but I guess it's more of a curiosity to put on your coffee table. So, and they've published previous books with the same idea, you know, the 51st Mersenne prime and the 50th, and going back. I think some of them might have actually been bestsellers, believe it or not. So the GIMPS project is what happened here is the first few Mersenne primes were found by hand, even before, of course, before the advent of the computer, and then people used computers, and then supercomputers, and then it became even too much, given the size of these numbers, to compute with a supercomputer. So this GIMPS project is a distributed computing project where people can donate time on their personal computers, and then collectively it's a very powerful distributed computer. And if the next Mersenne prime is discovered on your, while your PC is running the algorithm, you get some credit and your name gets listed, I guess, was the discovery. So I believe it's still something anyone can join, and you download some application, and then it does part of the computation for finding the next Mersenne prime. The other thing I wanted to mention is that this Mersenne prime, is also the largest known prime number. So it's not always the case. It's possible that there are prime numbers that are not Mersenne primes, but usually it's a Mersenne prime that's also the largest known prime number. And as we know, there's an infinite number of primes. And so let's continue. I have a few more facts concerning Mersenne primes, which I'll mention on the next slide. The concept of a perfect number is related to Mersenne primes, as I'll explain in a minute. Let me first define a perfect number. It's a positive integer that equals the sum of its proper divisors. Proper meaning we exclude the number itself. So I have a couple examples here. 6 equals its divisor, the sum of its divisors, which are 1, 2, and 3. 28 equals the sum of its divisors, which are 1, 2, 4, 7, and 14. You can add these, you get 3, 7, 7, 7 is 14, 14 is 28. The next two perfect numbers are 496 and 8,128. The concept was discovered very long ago, at least as early as Euclid's Elements from 300 BC. Euclid showed that if 2 to the p power minus 1 is a prime number, then 2 to the p minus 1 times 2 to the p minus 1 is perfect. 2 millennia later, Leonhard Euler proved that all even perfect numbers are of this form. So we have one example here. You notice 2 to the 5th minus 1 is 31, so that is prime. And it turns out if we plug that in, or use this formula here, 2 to the 4th times 2 to the 5th minus 1, we in fact get the perfect number 496. There's several open problems related to perfect numbers, even though they've been known for a long time. You notice here the perfect numbers, the even perfect numbers, are what we know about right now, because of this power 2 to the p minus 1. So anything of this form, of course, is even. What's not known is whether there's any odd perfect numbers. I saw an interview with someone a mathematician who was familiar with this, and he says even though it's been checked by a computer to an extremely large number, we haven't found any counterexamples. And the thought is that there probably is not an odd perfect number, but it hasn't been proven yet. And then the other open issue is whether or not there's an infinite number of perfect numbers. And we keep finding more and more of them, but they're extraordinarily large, and it takes a huge amount of computing power to find them. But again, the same interview that I listened to, the thought seems to be that there are an infinite number, but again, no one's been able to prove that yet. So I have a few links here. I'll put them in the description of this video so you can just click on them if you're interested. But there's a Wikipedia article on perfect numbers. There's a list of Mersenne primes and perfect numbers in again a Wikipedia article, and it's quite huge numbers. They list just the powers of 2 and not the number itself, as you saw from a few slides ago. The numbers would take a huge book to list, but they list the form of the number using the formula we noted on the last slide. And then there's a very nice video on this topic by Veritasium. It's actually one person, but he uses this name for his videos. It's called The Oldest Unsolved Problem in Math, and he's kind of referring to the problems I mentioned on the previous slide. And again, I'll put this link in the description so you can click on it if you're interested. I mentioned Leonhard Euler previously concerning the perfect numbers. So I thought I'd give a little bit of bio on Euler. He lived in the 1700s from 1707 to 1783. He was from Switzerland, mathematician, physicist, astronomer, geographer, logician, and engineer, who founded studies of graph theory, topology, and made discoveries in many branches of mathematics, including analytic number theory, complex analysis, and calculus. He didn't discover calculus, as we know that's credited to Sir Isaac Newton and Gottfried Leibniz, but he contributed to some of the early work on calculus. He introduced a lot of mathematical terminology, which we still use today, including it was his idea to use the Greek letter pi for the ratio of the circumference of a circle to its diameter. And he's known also for his work in mechanics, fluid dynamics, optics, astronomy, and music theory. So he was a very, very prolific writer, hundreds and hundreds of papers and work that I think took years after he passed away to just publish everything. I have a couple of references here. One, the Wikipedia article has some background information. Then there's an article from the Irish Times, Euler, a mathematician without equal and overall nice guy. So I'll point you to that. This is a fairly short article. I'll put these links in the description to this video. A little bit more on Euler on this slide here. Here's a portrait of Euler. At the time, my understanding is people would wear hats like this, especially when the portrait was being drawn. And as I alluded to in the previous slide, he was prolific. He wrote around 800 articles and books, half of which after he had gone blind. Euler had a photographic memory. He could easily remember poems, essays, novels, word for word. One of the popular stories was he could recite Virgil's Aeneid, which is almost 500 pages long. He could even tell you the pinpoint what page and from what edition of a book a paragraph came from. It's hard to believe anybody could memorize a whole book like that, but apparently he had that skill, as well as all the other things we mentioned on the previous slide. He was also known as a generous and kind person, which I guess is maybe not typical of some geniuses. And the article I alluded to on the previous slide from the Irish Times is kind of on this topic here about his disposition. So even after he had gone blind, he still was good-natured, and obviously he continued to work on as many articles and books even after he had gone blind. The handshake puzzle. This is from a book, Arithmetical, Geometrical, and Combinatorial Puzzles from Japan. And let's have a look at it. It's a fairly hard puzzle, but feel free to pause here after we talk about it a little bit and see if you can solve it. I can tell you I wasn't able to solve it. I needed to look at the answer, and even after I looked at the answer, it took me some thinking to make sure I understood it correctly, but we'll go through that. Let's first talk about what it is. So in a group of 6 children, each handshake is between a boy and a girl. Each of 4 children shakes hands with exactly 2 others. Each of the other 2 children shakes hands with exactly 3 others. Do these 2 children in this group here shake hands with each other? So a lot of precision in the way this is written, and it's quite easy to assume things here. So they're not telling you anything about whether the 4 children are boys and the 2 are girls or not. So don't make any assumptions there. There could be a combination of boys or girls in either one of these groups. And then where it says the 4 children shakes hands with exactly 2 others, it doesn't mean it's necessarily with these 2. It doesn't say that. And it says the 2 children shakes hands with exactly 3 others. Again, it doesn't necessarily mean it's 3 out of these 4 here. It could be with each other and then with 2 of the out of the 4. In fact, the question kind of implies that possibility, right? Do these 2 children shake hands with each other? So if you want to pause and think about it and come back in a few days, that's great. Otherwise, I'm going to go into the solution starting on the next slide. Let's look at the solution to the puzzle. This is going to take 3 slides to go through it all. We're first going to eliminate a few cases, but even before that, let's set some parameters here. So let B be the number of boys and G be the number of girls. And this is a symmetric problem, so we'll just assume without loss of generality that the number of girls is greater than or equal to the number of boys. The total number of handshakes, we can compute that. So the group of 4 makes 2 handshakes each, and that gives us 8. And then the group of 2 makes 3 handshakes each, so that gives us 14. And then since each handshake involves 2 people, we have to divide by 2 to get a total of 7 handshakes. If the number of boys is 0, then there couldn't be any handshakes at all because we only have handshakes between boys and girls. So that's a contradiction. So this case is excluded. And this little symbol here means contradiction. If there's 1 boy and 5 girls, then the best we could do is have the 5 girls shake hands with the 1 boy, but then that only gives us 5 handshakes at most, and that's another contradiction to this 7. If there are 2 boys, then they must be the ones who shake hands with 3 others, so they're in the group of 2. It couldn't be the girls because the girls would have only possibility of shaking hands with 2 others, and that so they couldn't be in the group of 2 that shakes hands with 3 others. So each boy, so in this case here, there would be 2 boys, 4 girls. So each boy shakes hands with 3 girls since they're in this defined group here, and then you would get 6 handshakes and not 7. So again, we have a contradiction. And so that, and given that our assumption here that the number of girls is greater than or equal to the number of boys, and the analysis we've done here, we need to conclude that the number of girls equals the number of boys equals 3. So there's still a couple of cases to consider here when the G equals B equals 3, and we'll look at that in the next slide. And then I'll give you an actual picture of the one situation that actually satisfies all the conditions. In the case of the number of boys equals the number of girls equals 3, we still have 2 subcases, and the subcases involve the group of 2 that shake hands with exactly 3 others. The two subcases are that the group of two are of the same gender, or the group of two are of different genders. The second case is actually the question we were asked, whether the group of two shake hands with each other. So we can figure that out by doing an analysis here. So we'll look at case one first. And that's this picture up here, this top line. So if the group consists of two girls, they each shake hands with the three boys, so that's 6. So their handshakes are all used up, and then this girl can't shake hands with these boys because they've used up their 2 handshakes. They're in the group that shakes hands with 2 others, and she can't shake hands with the girls either. So you get 6 in that case. And then it's completely symmetric if you have 2 boys in the group of 2 and 3 girls and a boy in a group of 4. By the same reasoning, you can only get 6 handshakes. So this case is out, and we have the last case here. If the group of 2 consists of a boy or a girl, then a valid solution is that they shake hands with each other and 2 of the opposite gender in the group of 4. So I have a picture, a little bit more detailed picture of that in the next slide. Let's take a look at that. So here's a picture of our case 2 from the previous slide. So the boy and the girl in the group of 2 shake hands with each other, and you notice this girl shakes hands with 2 boys, the boy shakes hands with 2 girls. So each in the group of 2 shake hands with 3. The lines mean handshake. So there's 3 handshakes here and 3 here. And the only other thing we need to make sure is that everybody in a group of 4 shakes hands with 2. So once we've looked at what the group of 2 does in terms of shaking hands, we still need to make a couple more. So this boy number 2 shakes hands with girl number 2, and boy number 3 shakes hands with girl number 3. And so everybody in the group of 4 has 2 handshakes. We don't have any boys shaking hands with boys or girls shaking hands with girls. So we've fulfilled all the stipulations of the puzzle, and we've eliminated all the other cases. So the answer is that, in the group of 2, the 2 members shake hands with each other. We have a geometry puzzle now, so a little bit different from what we've been looking at so far. So we have it turns out to be a square. These little double hash marks just mean equal area, so equal length. So the length here is equal to this length here, this length is equal to this length, and so on. So we have 8 different lengths along the sides of the square, and they're all equal. So we basically divided each side of the square in half. So we're given that. These are right angles here. This is a square, this is a right angle, right angle, right angle. And there's some point in the middle, we'll call it O, where we draw a line from that point to each of these midpoints. And we're told that the area of this is 20, the area of this here is 16, and the area of this region is 32. And we're asked to find the area of this region in here. So it's a tricky puzzle. You need to draw some additional lines and then work with triangles. So I guess that's the hint I'll give you. If you want to pause here, go ahead and give it a try. If not, I'm going to give you another hint on the next slide, and then we'll actually get into the solution of the puzzle on the slide after that. We have a hint here, or at least intended to be a hint. Hopefully it helps with the previous puzzle. We have 2 triangles, a yellow one and a green one. You see the green one's behind the yellow one. That's not important, but just wanted to point that out in terms of my drawing. So the yellow one goes all the way down to here, and they both have the same base, exactly the same length for their base. And then they have these 2 lines here. So the bases of both of these triangles is on this line M. and then there are other vertexes touching another parallel line to ML, and this height between the length between these two parallel lines, we'll call that H. And this notation here, L, means this is parallel to M. So if you recall, the area of a triangle is 1/2 the base times the height. And if I tell you that the area of the green triangle is 12, then you can conclude that the yellow has the same area, because the area of the green triangle is 1/2 H times B, and the area of the yellow one is also 1/2 H times B. They look different, but I mean, I could have pulled the line all the way out, this vertex all the way out here, and as long as it's touching this line, you would have the same height, and then assuming you didn't touch the base of the yellow triangle, you would still get the same area. So that's, it may seem simple on the surface, but it's something that you need to be cognizant of when you try to solve the puzzle from the previous slide. And just continuing with the same idea here. Again, you have two triangles, red and blue. Now they're not sharing the same base, but their bases of the same length. So this is B and this is B. They're both of length B. And the two triangles have this common side, and then they meet at a point up here, a vertex here. So the height of both of these, again, is the same, right? It's basically, if you drew a perpendicular down from here down to here, you would get the height of the red one and as well as the height of the blue one. And so again, using the formula, area equals 1/2 the base times the height, both of these triangles have the same area. So that's another clue in terms of the puzzle. Basically, you need to introduce some triangles that have the same area, and then work with the information we're given in terms of the areas in the puzzle. So again, you may want to pause here and give another try to the puzzle. If not, I'll give you the solution on the next slide. So we have the solution here to our problem. There's a lot on this slide, so let's take our time going through it. I recopied the figure from the original problem, and I added these dashed lines from each vertex to the point, which is not the center here, it's just the point off center actually. And so I've added these 4 dashed lines. Everything else I brought over. Then because it was getting busy in here, I moved the area numbers off to the side. If you recall, this along these solid lines here, this was 16. This area and this region here was 20. Then the area in this region was 32. So I just moved those off to the side. And then to remember, we were asked to find this area of this region here. That's the question mark. So the hint I've been building up to and giving you on the last couple of slides is now revealed here. If you notice, when we drew these dashed lines, these two triangles that we introduced have the same area. They have the same base. We were given that this length here and this length here is equal, and they meet at this point. So if you kind of turn this counterclockwise 90 degrees just to fit with the figure from the previous slide, they have the same height, so that means that both of these are the same area. And you look at this one here, again, you have two triangles, they both have the same base length, and their height is the distance between this line and this point. They both have the same height, and so they have the 1/2 base times height equals area, so they have the same area. Have the same deal here for these two and for these two. And so from this, we can write down some equations. A plus D is 16. We were essentially given that this whole region was area 16, but now we've broken it into these two triangles. So a plus d is 16, a plus b is 20, b plus c is 32, and we still don't know what d plus c is. That's our question mark. But we have this general equality here, and this is independent of the problem. But let me just explain this here. It's pretty straightforward. You have a plus b plus d plus c. So these are just real numbers. So from basic algebra, we can take the d here and put it with the a, and the b and put it with the c. That's just the commutative law for real numbers and the distributive law. We've just rearranged these. That's always true, independent of our problem. Why did I do this? Well, I did this because we know what a plus d is, and we know what b plus c is. So we can, and we know what a plus b is. So we know we know this quantity here, that's 20. We know a plus d is 16, and we know b plus c is 32. And lo and behold, the one that we don't know here is d plus c. That's the one we were looking for. So we plug in those numbers, 20, d plus c, we don't know yet. We'll know in a second. 16, a plus d, 32 for this. And then we just add this, and we get 48. Subtract the 20, and we get 28. So what looked like a problem that was insolvable was in fact solvable just by this insight here, which, by the way, I did not figure out myself. So it takes a lot of tinkering to come up with that and some imagination. But with this insight, and then just this basic property of triangles, if they have the same base and height, they have the same area, and then plugging things into this formula, lo and behold, we get a solution. So an interesting problem. It just, from the standpoint of going over some basic geometry, it's I think it's interesting. But the clever approach of putting in these dashed lines is, is quite interesting, and leads us to what looks to be a simple solution once you know how to do it. You may remember the Pythagorean theorem from high school geometry. It's one of the better known theorems from geometry. So it's pretty simple. If you have a right triangle, in other words 90 degrees, a square edge like we have here and here, then the square of one side plus the square of the other side equals the square of the hypotenuse, the longest side. You can see here that it doesn't require any particular length. You can stretch this out as much as you want, as long as you still have this right angle here. Then the square of a squared plus b squared equals c squared for all possible right triangles. And I have a couple of examples here. We have the famous 3, 4, 5 right triangle. So you get 3 squared is 9, 4 squared is 16. That's the sum is 25, and that's 5 squared. A little bit more complicated is the 5, 12, 13. So you get 25, 144. You add those together, you get 169, and that's 13 squared. So the reason I introduced it here, I want to show a proof a little bit later on, but I needed some background information first. And so I thought I would at least remind everyone of the theorem, and then give you some background information. Then I'll show you an unusual proof of this fact. A trapezoid is a four-sided figure with two parallel sides. They could be of different length, and then you can have different angles here, as I'm showing in this examples. There's also different definitions of trapezoid, and sometimes it's called a trapezium. So you can, for example, look in Wikipedia, and it'll show you a whole bunch of different definitions. So apparently the mathematical community hasn't standardized on one, but we'll go with what's here, just needing the two parallel sides, and then the angles don't need to be right angles or even equal to each other. And what I need to use later on is the area formula. So we'll kind of give a rough sketch of how we get that here. If we take this trapezoid and then just flip it and then twice, once horizontally and once vertically, so that you have basically this shape but flipped in horizontally and vertically, and then you put it next to the original shape. And so this side here plus this side here is equal to this side and this side. This is length B, and this is length A, this is length A, this is length B, and we haven't changed the height, so we have to change, it's the same height. So what we have here is a parallelogram. This angle is equal to this angle, this angle is equal to this angle, and the top and bottom are equal in terms of length, and the two sides are equal in terms of length. So we have a parallelogram, and the area of that is just the height times the sum times the base, which is this A plus B, the way we've constructed it here. And the area of the trapezoid, of course, is half of this. We just took two trapezoids and put them together, and so the area of a trapezoid is 1/2 the height, and then you sum the top and the bottom, and you get this. We're going to use this formula later on, so that's why I've developed it here. James Garfield was the 20th President of the United States. The reason I mention him here is he's also a mathematician, and he published the proof of the Pythagorean theorem in the New England Journal of Education. I have the reference here. At the time of the publication, he was a congressman from Ohio. He became president in March of 1881, but he was assassinated only a few months later and died in September of 1881. Garfield was the only president to have published a work of mathematics, as far as we know, and his proof appeared in a book, The Pythagorean Proposition. It was proof number 231 out of a compendium of 370 proofs. I think there's even more proofs, different proofs of the Pythagorean theorem. It seems to be a very popular hobby for some folks to try to prove it in yet another way. For those of us from New Jersey, it might be of interest that Garfield died in Elberon, New Jersey. That's along the coast. And he was sent there after he got shot to recuperate, but I guess at the time they didn't have the antibiotics that we have now, and he died from the infections resulting from the 2 gunshot wounds. So let's get to his proof on the next slide. So let's have a look at the proof from Garfield of the Pythagorean theorem. He started with the right triangle, which is the solid line here, has side lengths A, B, and C, and then he took this triangle, he duplicated it and rotated it, so you see this angle appears up here now. Maybe I should draw in the other angle. So this angle here is the same as that angle there. And then he connected this vertice with this vertice. It's a straight line. And so what's left on the outside is a trapezoid. We'll use that fact in a second. I just wanted to point out this triangle in the middle is also a right triangle, because the sum of the angles of a triangle is 180. So this angle here plus this, and this is 90, of course, and then so this angle and this angle together must be 90, and this angle is the same as this angle here. So this and this are 90, and that leaves just 90 degrees, since we're talking about the 3 angles making up a straight line, which is 180 degrees. So this triangle in here, A, B, D, is a right triangle. And so the trick is to sum up the areas of the trapezoid in 2 different ways, and that's what I'm going to show you down here. So the one way is to use the formula we developed earlier for the area of a trapezoid. It's the height, and this is kind of turned 90 degrees from the picture I drew earlier for the trapezoid, but let's say this is the height here. So that's A plus B. Then it's 1/2 the sum of the top and bottom. Again, this has been rotated 90 degrees. So it's 1/2 A plus B plus A. So this here. So that's one way of getting the area of the trapezoid. Then the other way is to sum up the three triangles here using the formula for the area of a triangle. So this triangle here is the area is 1/2 A times B. And then this is the same triangle, so again it's 1/2 A times B. So it's this term and this term. And then this has the base is C and the height is C, so it's 1/2 C squared. And then from here we just equate these two different ways of computing the area of the trapezoid. So this equals this. And when you multiply this out here, you get A squared, or 1/2 A squared, plus AB, plus 1/2 B squared. And so the 1/2 here, the 1/2 AB here, and 1/2 AB here, you subtract that from the AB on this side, and you're just left, and then multiply the whole thing by 2. Sorry for leaving out a few steps, but I was running out of space. And then you're just left with C squared here and A squared plus B squared on the left, and you have our solution. So quite a clever proof from Garfield. As I say, it was published in a journal, and he did this while he was still a congressman. Okay, so that's the last puzzle in our lesson, and the very next slide has the solution to the prime number puzzle I gave earlier on. So have a look at that if you haven't found the solution already. Here's the solution to our problem from earlier in the lesson. Recall that we needed to have this row, this diagonal, and this diagonal all adding up to 41. So we can check a few of these here. 5 and 19 is 24. 24 and 17 is 41, so that works. 17, 13 is 30, and 11 is 41. 23 and 7 is 30, and you get 41 again. And then 23 and 13 is 36, and 5 is 41. So they all work. I don't think there's another solution, but you might want to check and see if it's possible to get these all to add up to 41, or even add up to a different number. I don't think that's possible either, but this is at least, I think this is the unique solution, but I didn't try to see if there were any other possibilities.